Start by wishing everyone a happy new year, and for me it's a pleasure to start the year with one of the first lectures. Eliezer told me, well, it's a New Year's Day everywhere else, so this is probably going to be one of the first lectures on the planet. So I'm going to tell you the next thing. Today I want to get to the dark matter ideas, and I will summarize a little bit the things I said last time, and then towards the end, I will describe indeed how, well, what I've been talking about can be related even to observations. So the basic thing I want to summarize is that the way I view that gravity can be understood from an underlying system is to think about that underlying system as a dynamical system. I mean, I've described examples in string theory, but what I like to do is sort of think about those examples as being typical for the way we, well, have to apply to many situations. So in the examples I described, I talked about the microscopic descriptions of black holes. And there we know the microscopic phase space because we have verification both on the gravity side as well as sort of a microscopic picture. And this dynamical system that's really, so there is a Hamiltonian associated to it. It has certain equations of motion. I'm not going to go in too much detail again about how to describe that. But I'm going to think about this as what I call the Higgs branch. I understand that this is not a very familiar terminology to most of the students maybe, but so this afternoon I may say more about this in the tutorial, and I'll refer to some literature on this. But the essential point is that in this formulation we don't have any immediate interpretation in terms of the space-time coordinates. Even the matter that we normally think about is not sort of directly visible in the Higgs branch. So in a black hole, it's really describing everything that's behind the horizon. And if you want to describe particles, then you have to think about a different phase of the system. So this is like a phase of the underlying system in which there's a certain field, which I call H, which has a non-zero expectation value. When that is happening, the coordinates that we normally associate to particles cannot move freely, and the things are bound to their locations. But I think the interesting thing comes when you start thinking about matter, which you take out of this, and then we have to describe this in terms of this dynamical system. So the two essential things that I need for this dynamical system are, well, there's a Hilbert space, and let me call this H. But this Hilbert space depends also on well, it has a certain size, but it also is associated with a number of excitations. So what I'm going to describe now is very general. I mean, I'm not going to make very specific statements, as I said, but I'm going to assume that there's a number of excitations which I call n. I'm going to be more specific about what this number is. And you can roughly think about this Hilbert space as then being a product. I mean, if you think about n particles, you generally think about the Hilbert space as being a product space. In string theory, we see something similar happening. You can think about the space, say, with one excitation, and then you take sort of the nth product. But now you have to symmetrize. That means you sort of divide out your Hilbert space by permutations of those n objects. Now this space is not the this is how we would do it normally in particles. Actually, in string theory, this is not entirely how things work, because if you think about this, Hilbert space is too small. However, for the phase space, it's sort of a similar, we can do the similar thing. So let me replace Hilbert space by phase space, and then this is sort of a more accurate description. The phase space for n objects is indeed sort of the nth-fold product of single ones, and then modded out by n, because actually what happens here is that if you look at a space where you mod out by a symmetry group, you can add, well, if you divide out by symmetries, you generally can have fixed points, which sort of like orbifold points. And it turns out that in the Hilbert space there are sectors or states that are associated precisely with the fixed points of this permutation group. So this is a permutation group of n elements. And so in order to get the correct counting, and this is sort of what I described last time briefly, you have to sum over all possible permutations. Or I hope so to say, fixed points are generally characterized by elements of the permutation group. So how do you parameterize elements of a permutation group? You have cycles. A permutation of n elements has cycles of length n in such a way that the number of cycles of length n, if you add it all up, must be equal to the capital number n. So this is a much bigger, this is all kinds of sectors labeled by any set of numbers n satisfying this condition. If you then look at the dimensionality of this Hilbert space, if I know the dimensionality of the single Hilbert space, which I call C, then the dimension of this Hilbert space is just by combinatorics can be calculated. And this is what I described last time. We have dimensionality of the big Hilbert space, which is like the related to the entropy, is then written as roughly, I'm not going to put in too much detail here. It's like a product, it's like a Cardi formula where you think about C really as the central charge and N more like L naught. So this is a dynamical system from which I want to derive now another set of variables. We want to think about eventually how matter appears and how indeed space-time appears. And it arises from another phase which is called the Coulomb branch. So we want to go from the Higgs branch to the other phase, the Coulomb branch. And just generically, this must be described by matrix valued, first of all, matrix valued coordinates that we start from. We know this in string theory because this is how we describe D-branes. So I think about these coordinates as n by n matrices. And so the n that appears here is going to be related to the n of this, the size of this matrix.
Excuse me?
Yes?
I have a very simple question. Where do these 2 pi in the formula for the dimension of the Hilbert space originate? I only see like integer valued
numbers.
Yes.
So if you do the combinatorics here, you have to count how many partitions there are. And then you do this through a partition function. And then what you're interested in is counting the degeneracy of those partitions for very high n. And then there's actually a trick. It's the Hardy-Ramanujan formula. It's what mathematicians used. They used the modular invariance of this partition function. And then by going through the steps I did last time, sort of the saddle point approximation there, you find that the saddle point, so the growth of the number of partitions goes exactly with this 2 pi. So it's counting partitions.
I think he's worried that the right-hand side is...
Oh, sorry.
You can have small corrections.
I think I even said it wrong here. It must be the logarithm, of course. Thank you for that. And actually here it's here actually it's correct. So you go from indeed the dimension of the single one to a dimension which is asymptotically for large n. So this should be thought of as being the entropy. Now the Coulomb branch is not just described by these matrices. Actually, the Coulomb branch is a further condition. So this would be coordinates of your particles. And in order to see space-time appearing, you would have to impose that these coordinates commute. So the Coulomb branch has this further condition that xi and xj commute. And then these become matrices which have eigenvalues and these describe then the positions of your excitations in space-time. But before they commute, I mean, if you think about the situation still where this is non-zero, then there would be off-diagonal modes. And we know in string theory, these describe the strings, or they are associated with strings that go in between different positions of the d-branes. I should, well, we can label the eigenvalues by number alpha, sort of, which goes from 1 up to n. Then this would be an off-diagonal element would have two different indices, and then by integrating them out, we generate the gravitational force between those objects. But in order to go really to the matter on space-time, we have to impose this condition, and this is what's called the Coulomb branch. Now, what I want to argue now is that indeed in describing real systems, that we should think about a situation where we have both a Higgs branch as well as a Coulomb branch together. Because generally what you have to impose in order to go to the Coulomb branch is that this expectation value of the field here also has to be 0. So this field, by the way, I can think about as having indices also in a representation of un. So n here. So this is a matrix, so you can think about it as an element of un. And actually it's in the adjoint of un. But the variables which I started from can also be in the fundamental representation. And so if the expectation value of such a variable is not equal to, well, if it's not equal to 0, actually it turns out that these eigenvalues cannot move freely, but if it's 0, then it can move freely. Now it's interesting to think about a situation where part of the expectation elements here have a non-zero expectation value and part of them have a 0 expectation value, because then you get in this mixed Coulomb Higgs branch phase. And I'm going to argue that this is what we're going to need for understanding, well, things like what is matter, and also what's dark energy and what is dark matter. So matter is going to be built out of these objects on the Coulomb branch. So this is going to be the way matter will appear. And the Higgs branch is going to describe something we don't really see. I mean, this is, for instance, how we describe black holes. Indeed, behind the horizon are described in terms of the Higgs branch. But particles then are the things that enter the Coulomb branch. So to set up a little bit that, let me think about a thought experiment. Yes? Sorry? What force?
Force between matter particles.
Yes. You're asking about what? About the gravitational force among particles? What it comes from? Yes. So well, this is how I described it last time. I mean, there's the microscopic formulation really has to be thought of as being on the Higgs branch. So there is a microscopic phase space, and these variables have been derived from it. And what I showed last time is that we have to integrate over the variables of the Higgs branch in order to even generate the action for these Coulomb branch variables.
So that you get some action.
Well, but there is actually
Scalar potential for the axis. This is what is associated with the force?
No. So last time I described some more general principles in the following way, that if you have a fast dynamical system, and I think about these variables as being the slow variables, there will be a reaction force on the slow variables due to the fact that you change the state of the fast variables. So the fact that we have an underlying system the forces between the particles here are really totally induced by anything that happens on the Higgs branch. So even inertia, as I'm going to argue, is actually a force that you should think about as a force being induced by the variables on the Higgs branch and the way that these particles will influence them. And so let me actually make that more clear by going through a thought experiment. I'm going to think about a black hole. So we have a black hole and we want to describe this microscopically in terms of the Higgs branch variables. So I'm going to say this is described by a set of variables, and I'm actually going to think about really very much a string kind of setup. So this is described in terms of the Higgs branch. So how do you think about the Higgs branch? I like to think about it in this picture. I mean, if I think about the matrix X as being n by n, the Higgs branch can be thought of as being a fundamental. So the Higgs branch, let me indeed think about this as having fields which are in the fundamental of un. That means they have n by some other number which I called k the last time. So my Higgs branch variables are here. And here I have the conjugate. So you can think about them also as matrices, but they're not rectangular, but they have k by n. And in order to be able to describe things here in terms of the eigenvalues, I need to have that the expectation values here are non-zero. But if this expectation value is it has to be 0. So what I mean by a mixed Coulomb-Higgs phase is that the expectation values of these H's are non-zero in part, but they are 0 in another part. And then if you look at the matrix here, part of this matrix can indeed be on the Coulomb branch, namely the eigenvalues can sit here. But in order to identify this part, I have to indeed impose the fact that these expectations values are 0. So how does this appear from a black hole situation? It's where you indeed think about particles that I take out of the black hole and say put them in a box. And so lowering particles into a black hole is like lowering this part of the matrix into the bigger one, and where you really eventually get the expectation values here to be non-zero. So let me represent this in terms of strings. I mean, the strings between particles in the box, that's describing the matrix in here. But there are also, if I think about this as being formed by strings which were collapsing, that matter is basically described here. But all of those degrees of freedom eventually entered the Higgs branch, which is sort of described in these variables. But you can still see sort of the strings that would stretch between whatever was in here and the particles inside the black hole. You can either think about this as being these elements which I have here, or actually, because I am actually not using these variables, I'm using the Higgs branch variables. They're actually related to the same variables which I have here. So there's actually a part of the phase space. Maybe I should make it more clear. I mean, there's a coupling between the variables here in the Higgs branch and the variables x in such a way that if I move my particles out of the black hole by removing them away from the bound state here, I'm forcing these variables to have 0 expectation values. But when I lower it into the black hole, these things can start acquiring their expectation value again, because then I'm forming the bound state of these particles with the entire system. So gravitational collapse is the same as making the transition from the Coulomb branch into the Higgs branch. The Higgs branch describes the black hole, and this describes the matter that's outside. But it has to go through 2 steps, namely the eigenvalues they become sort of part of a non-commutative set of matrices, which so you're going to actually enter a phase where this matrix X is not just diagonal, but it can also get sort of in the first a non-zero expectation value. I told you last time this is related to the fact that there could be membranes formed. And then it may enter into the Coulomb branch, sorry, the Higgs branch. So this is gravitational collapse, but the other direction is where you take these particles out, is how you form matter from the Higgs branch. This is indeed, people have thought about this in thought experiments, namely if you know that the black hole has a finite temperature, you can take a bucket, you go to the horizon of a black hole, and you take out your particles, and then you take the bucket out, and you will find particles, really matter, in your system, but you started with something which was just space-time with a black hole in it. So this actually makes clear that you can get matter out of the Higgs branch by some procedure. For me, this is an indication that this is the way we should think about the matter in our, even in our universe. There may be an underlying system which is like the Higgs branch, and that the matter we see is basically has escaped the Higgs branch onto the Coulomb branch. And then the forces we see, and in particular inertia, is going to be related to the interactions of what I have here and this Higgs branch. Because let me now make the analogy with the polymer picture that I had. I described for you what I called an entropic force. The entropic force is where you have a heat bath and you have a polymer in here, and you're putting a bead here and you want to measure the force. Now the force here arises because if you lower this in here, the polymer can shrink and get more entropy. You're actually increasing the phase space of this polymer. The same thing happens here. I mean, because the phase space associated to this polymer, you can think about as the phase space carried by these elements of the Higgs branch. And if you want to lower the particle, you really means that the distance between, well, these eigenvalues here and the eigenvalues there, you're reducing it. And that, because of this coupling, will enhance the phase space of the Higgs branch. And this is sort of the thing that pulls in the particle into this. Here in this case, yeah, it's an entropic force, but here it's actually pulling the particle into the black hole. And we know that eventually this is the same force that we would call inertia. Yes?
In the case of gravitational potential, we have a very important property, which is superposition. So the force that a test particle feels from n particles is the sum of potentials from.
That's correct.
How does it work from the entropic point of view?
I will make that clear in a minute. I mean, it's going to be very clear from the description I'm giving here. I mean, because I mean, I think I already said part of it here. Each of these excitations will have the same mass, and the gravitational force between the excitations here comes from integrating out the off-diagonal modes. So let me just put it in two blocks in here, and ask what's the force between them. You'll find this is related to the size of this block. And I'm going to argue for you that the size of this block is determined by the mass of the object. And this is the size of this block is going to be related to the mass of this object. So this has mass, say, m1, and this m2. But this product, this phase space has a size which is the product of m1 and m2.
But then you add the third mass. Does it work?
It's linear.
It's linear.
I mean, if I threw a block like this, I mean, if you do whatever, I mean, you can ask, what's the force between each of these blocks? It's determined by the size of the block connecting the two, and that has a size, which is the product of these two. So the number of eigenvalues is going to be related actually to the mass of the objects, and that's exactly where I want to get at. because indeed, in a minute, I want to relate this to observations because I want to tell you what is this number n and what is this number c. But let me continue with that thought experiment because I'm going to make it a little quantitative. Actually, it's a thought experiment that started all of this because it's Bekenstein's thought experiment on black holes, where he wanted to argue about that black holes have an entropy, but also deduce something about the entropy of a system of a certain size. If you have a black hole and you have a box of size r, and you have a certain mass m in it, you can ask the question, what's the maximal entropy that I can put in this box? And the argument goes as follows. I'm going to lower the box towards the horizon, and at the horizon I know there's a certain acceleration, g. So that's the force. So if I want to lower the box, I have to put some, and do it gradually. I have to attach a rope to it, and then gradually lower the box into the black hole. Now, let me imagine putting the box very close to the horizon and then ask how much energy is still in the box. If you put a box on the horizon, it's totally redshifted and there's no energy in the box. So the energy that you have to associate to the box, or the energy that you sort of put into the black hole, actually by dropping the box into the black hole, is equal to the amount of work that you do when you pull out the box precisely a distance r. So there's work which is equal to the force times r. Well, the force is just m times the acceleration. And then we also know that there can be then a change of the energy of the black hole, but this is by just the first law of thermodynamics equal to the temperature times the change of entropy of the black hole. So if this box would have contained a lot of entropy, you would actually drop the box into the black hole and you don't see anything of the entropy of the box. But you will have increased the entropy of the black hole by this amount. So the argument is that this box cannot contain an arbitrary high entropy. It should be smaller or equal to whatever I'm calculating here. Because I know what the temperature is of the black hole. The Hawking temperature of a black hole, where the acceleration at the horizon is equal to g, is equal to g over 2 pi. If you put in constants, there's an h bar, pi and h bar and a c here, but let me just work with those constants equal to 1. So you know that the temperature is proportional to the acceleration, and here I also have this acceleration in what I have in here. So what you get is that there's an easy way to calculate delta S. It's equal to 2 pi times m times r. So this is called the Bekenstein bound. So m times r is actually going to be, for me, the number of eigenvalues, number of excitations that I can put into the box. So the fact that there's a maximum entropy already tells me also there should not be an arbitrary number of possible excitations in here. So this thought experiment was just done using arguments of gravity, but we have some idea what the microscopics may look like, and actually for me it's a way of restricting this number n.
It's the number of states or it's log?
It's a number of excitations, and so I'm thinking about them as, say, all right, I think we should talk about them as sort of gravitons. So they're like massless modes, and you want to know how many can you put into a box of size r. You know that the lowest frequencies that you can put in go like 1 over r, and so you have to divide your energy up in so many bits, and the number of excitations that you can put into a box of size r is roughly of this size. How am I doing on time? Yeah, I think I want to get actually to the...
This is the bound, right? You mean greater?
This is a bound, you're right. This is a bound, but this would be the change in entropy of the black hole.
So I'm just wondering, in a regular field theory, the entropy anyhow goes to a power of the energy which is smaller than 1.
Yes.
It's only in string theory that you get that it goes with the energy of this black holes, that it goes higher. So what do you think is the power actually of this?
I think actually what I'm saying is that okay, I'm thinking about okay, I want to start from the microscopics. And I want to think about how the matter that we have in the box arose from a microscopic point of view. And then I'm thinking about this picture of how we get things from the Higgs branch onto the Coulomb branch. And I'm thinking about, like in matrix theory, where we think about everything almost built up out of these gravitons. So for me, these are like gravitons. So lowering a box towards a horizon, we really keep it there for a very long time. The temperature at the horizon is locally divergent even, because if you from infinity has a finite temperature, and the argument I gave here is from infinity. But locally, you're heating up the system to the highest temperature it can almost go. So you're breaking up everything in the smallest bits that you have, which I think are gravitons. And so then you ask how many of those can you put in. Then you get to this number. And I think we should indeed think about the string theory way of doing this by thinking about anyhow, this is for me an additional argument why this number actually is the correct way of counting this number of this size. I have more arguments which I'm not don't have time to really explain in detail. Maybe if I have time at the end, because what I want to get to now indeed is sort of the dark matter ideas. So I'm going to leave this now as a way as some idea. And I want to relate it to observations. Oh yeah, maybe I should say one more thing before I go there. Actually, it's related to the question that was just asked. Precisely what I said here, namely, if I think about a system of two masses, m1 and m2, the force between it is, as I told you, due to the fact that I'm integrating out these off-diagonal modes. There's a certain amount of energy also in this system, and then I can deduce that from the way we think about gravity just in normal Newtonian gravity. So this is quite Newtonian in my interpretation. Normally you would couple the Newtonian potential to the mass, something like this. And here you do the same thing. So this includes the Newtonian potential of this mass at the point sort of this mass, and you multiply the two. And here you do the same thing. This would be double counting in the sense you would take into account the potential of this one for this, and you also the potential of this. Actually, these two are actually equal because you know that the potential is basically an expression in terms of gm over, say, the distance r. But the total energy is only 1 times this or 1 times that. But what you can add to this is actually the energy in the gravitational field in this system. So if I think about the gravitational field as the gradient of the Newton potential, like the gradient of an electric potential, then there's an energy, the gravitational energy, which is 1 over 8 pi g integral of grad phi squared. It's like what you do in electric fields. You also have an an energy in an electric field, which is basically the square of the electric field with 1 over 4 pi epsilon 0, of 8 pi epsilon 0. So this energy is actually also there. And if you calculate that energy for the gravitational potential of both of these masses, this would be giving you exactly a positive contribution, but together it represents the total gravitational energy. Now, the reason I'm going to mention this is that this I'm going to interpret as the gravitational energy that's contained in. So I'm thinking about this indeed in a matrix language. Where's the eraser? Yeah. So I had my picture in terms of the eigenvalues describing whatever the matter. So the energy associated with the mass and everything is contained here. But the off-diagonal modes contain an energy as well. And I'm identifying this with the energy in the gravitational field. And I'm now going to think about precisely this situation where we're lowering a box into, say, a black hole. Then this box can be described by the matter describing in this matrix. But then I have to take into account also the degrees of freedom associated with the black hole and the fact that there is a temperature and things like that. This will be where the ideas about dark matter will come from. But what I'm going to do actually is now going to tell you about dark matter and why I think these ideas are related to that. So we're going to think about our universe. Yes, I'm going to erase this. Let me first think about dark energy, or just a universe which has a positive cosmological constant, because we know that we have in our universe something which has a positive cosmological constant. So we can think about living in something like the Sitter space. And this would be the situation when we only have dark energy. The Sitter space has a metric which I'll write like this in what's called the static coordinates. That means we put ourselves in r equals 0, and the horizon we have, so we're in the middle of a coordinate patch, which is called the static patch, because there's static coordinates. There's just time translation invariance, so I have a finite energy. I can define a conserved energy. We put ourselves in the middle of it, and then there's a horizon when this number becomes equal to 1, because then, as usual, this defines the horizon. So the horizon is at a distance r equal to 1 over h0. There's also a, well, if you have a horizon, you can actually do the same things as you do for black holes. You can define a temperature, and you can even define an entropy. So the entropy will be equal to just the Bekenstein-Hawking entropy, and the temperature is equal to the acceleration, again, so through a formula like that, but the acceleration now at the horizon. And this turns out to be equal to this. I mean, the temperature is h0 over 2 pi, and that means actually this acceleration, if you calculate it, it's actually, if you put in the constants, it's c times h0. So this is a way of thinking about the Sitter space, and it has an entropy, it has a temperature, but we don't see any matter, we only see sort of a cosmological constant. I'm going to think about this as being described by a microscopic system. For me, this is the Higgs branch. So if we want to get matter out of here, we want to put something in here, but then we have to describe this in terms of particles on the Coulomb branch. Now, what I'm going to describe to you about dark matter will actually make clear that the picture I'm describing here, which may have sounded sort of a little vague, actually has evidence in observations. Did I forget something here? I think I'm okay. So I'm now going to get to dark matter. Yeah, so the situation I described here with black holes sort of arises here with the matter inside the Sitter space. So many of the things I said here will actually apply, and it's actually how we observe things.
So at this stage, you're imagining some,
this is already a product. This is already. So this is you're trying to describe a background metric for the universe in terms of some microscopic degrees of freedom, which you said are the Higgs branch.
So I'm saying.
You've described how the metric or space-time.
Okay, yeah, let me try to make that a little more precise. I'm thinking now there is a microscopic system, which is the Higgs branch. There's no space-time yet. And so it's entirely just a dynamical system, and it has a phase space volume, which I eventually going to associate to this. But what I'm going to do now is think about particles that can arise from that system. And now the first particle that I get out, I can ask what geometry does it see? Because that's going to enter into the Coulomb branch. So the geometry that I'm describing here is the geometry of the Coulomb branch. So I have a microscopic system from which I can derive a... Eventually I want to get to some matrices X, and they have eigenvalues little x, and if I integrate out degrees of freedom of the Coulomb branch from the Higgs branch, I get a geometry, and that geometry should be the Sitter space. And even the inertial force of a particle in here should be obtained from integrating out those.
What guarantees, by the way, in this game, in the way of thinking that the geometry is independent of the number of particles you measure?
It's not.
And it's not because you say some of them are dark matter.
First of all, we know that matter itself starts interacting and creates gravity. And as I will tell, I mean, what I'm going to do now, I'm going to start actually this. So this is the picture where everything is first in the Higgs branch. So I had this way of representing it. I think about the states in here. So everything is now in the Higgs branch. And now I'm going to test first one particle out of it and ask what does it describe. Then I have to integrate out this little slitter of the Higgs branch. And that's giving me the inertial force. But now I'm going to make more matter appearing. And what I'm claiming is that it's impossible to have just matter on the Coulomb branch and everything else on the Higgs branch. There must be an intermediate phase, which is partly Higgs, partly Coulomb branch, which has the properties that H, so the Higgs branch has that H is non-zero. The real Coulomb branch has H equal to 0, but also commutators equal to 0. So there's going to be a phase in the middle, which H equals sort of 0, but this not yet equal to 0. And I'm going to calculate how much of there is, actually.
So what is the reason in this way of looking at it that we end up with a sitter? Just take it for granted.
Well, there's observation, but there's also, of course, the fact that there's a horizon. Frankly, I think about this quite geocentrically in the sense that we can put ourselves in the middle of our own observable universe. So whatever happens to the redshift... No, but I think there is an interpretation of the redshift which I'm going to be given. Because for me, this is like the place where I should put Newton's potential. So the expressions that I'm going to write down actually going to tell you what this object is. And so I think redshifts will come out quite naturally. But yeah.
A priori, in this picture, there's no reason why you wouldn't end up with flat space.
No, actually, no, I think flat space to me indeed is not a good system to start from. And clearly because I do need my underlying dynamical system. So the fact that this dynamical system has an entropy, has a phase space volume and a finite temperature, that already reflects the fact that we're going to end up with the Sitter space. I think I cannot describe Minkowski space in the same picture. So that's even worse, of course. So no, I'm not. I don't think that my description should allow every space-time. Although there, I mean, okay.
No, but
Well, of course, if I have the Sitter space, I can always go to a flat space limit. But this is really like taking sort of the temperature, which I have finite to be, go to 0. So what I'm going to do, also, what's going to be clear is that the amount of dark matter is going to be related to the fact that I am in the Sitter space. So the dark matter would disappear if there would not be a finite cosmological constant.
Still, along this line where I'm also not clear, do we start with all possible matrices in a given point in the Higgs branch, you know, and then integrate out stuff? Are you saying that there are just some of those which you want to start with, and then when you integrate out stuff, you end with the Sitter? Or what's going on with this? What about the starting point?
For me, the starting point is really the Higgs branch. And there's a microscopic system which I don't fully even may know, but I know what comes out of it. Namely, we can describe particles in our space, but they're derived from the variables on the Higgs branch. And then I want to know what's the effective dynamics of the particle on our space. That particle is moving on the Coulomb branch.
That would happen independent of what point you chose on the Higgs branch? You would get the same answer? Or would there be preferred points on the Higgs branch?
No, the Higgs branch to me has, I already said a little bit, this symmetric product structure, but I think really of the Higgs branch as something quite homogeneous. They can each eigenvalue is sort of, there's a big symmetry group acting on it. So which eigenvalue I take, that should not matter. Sorry? The permutations, that's right. And I also think that the description we're going to get, as I said, is actually putting us in the middle. So I think about emergence of space-time not just as a dynamical fact, it's also our own way of describing the physics that we see. We are the ones assigning a space-time interpretation to the things that we observe. So the emergence has very much to do with also the point where you start emerging from, or how you look at your cosmology. So I think emergence is also making clear that we are not having an infinitely precise description of what space-time is.
Usually people who deal with dark matter, the astrophysics community, assume that it's gravitational interactions, that it's just mass of some kind, and its gravitational interaction is identical to ordinary gravity. You seem to be saying that it is different because of the...
I haven't said anything about I've not said anything about dark matter yet.
You said it's non-commutative in the X-coordinate.
I'm going to tell you what dark matter is, and how it behaves is precisely as you say. But it's not a particle. There is a mass associated to it, and I'm going to calculate how much there is. And it's clear that it's going to come from the fact that we do have a Higgs branch and a Coulomb branch, and that what we call matter is the stuff on the Coulomb branch. What we call dark energy is going to be the energy on the Higgs branch. And there's going to be a requirement, a condition that's going to tell me how much dark matter there should be, because that's the stuff in between.
But you're still thinking in some sense of, try to put this in context of a Hamiltonian approach. And the question is whether the temperature, for example,
Yes.
the size of the universe, is coming out of parameters in that Hamiltonian, or choice of quantum state in the Higgs branch? Where is that?
That's a good, you say, is it the state property or is it a Hamiltonian property? Okay, let me speculate at the end about that. I think there's a relationship between the two. I don't think that we have a freedom here to put the system in an arbitrary state directly, but we can shuffle around energies and do something with the matter. But I think that the state, I mean, H. So
when you say, you have an equation, expectation value of H not equal to 0.
Yes.
Is that referring to ground state of some Hamiltonian system, or is it referring to some arbitrarily chosen?
No, we're not in the ground state, and actually it's clear that we're not in the ground state. And I think the ground state may look more like anti-de Sitter space. I think the fact that we're in the Sitter space also telling us that we have a dynamical system with an energy in it, and there is dynamics happening. So we're not in the ground state. And Now, let me actually now describe the phenomena that I associate with dark matter and how I'm going to relate it to these ideas.
Can I have a question?
Yes?
So, as far as we know, dark matter could as well be like another SU3, and SU2, that SU1 gauge theory, which is hidden, and there could be some dark field.
What I'm going to tell you about dark matter is going to make clear that that cannot be the case.
But my question is that from the astrophysics point of view, it may be one fermion which is massive, but it may
No,
also be a small gauge theory.
if you look at the data, look at the observation. Sorry, okay, go ahead.
So
Okay.
there could be dark people in some dark galaxies doing exactly the same exercise, and they would inevitably put themselves on the Coulomb Branch and reach exactly the opposite conclusion.
Okay, I agree. No, well, the conclusion I'm going to draw is going to not... no, that's not the right way to think about dark matter. I agree with the following, that what I call what's on the Coulomb branch and what's on the Higgs branch may be an observer-dependent statement. And then maybe what we do from our perspective. But it's not like it's determined by the matter that we made of. I mean, it's going to be very clear that there's not a possibility of interpreting dark matter as just some other form of matter. And actually, if you look at the observations and look what people see, I think it's very clear that that interpretation will not fly. So I'm going to tell you about those observations. Yes, and they have not looked at the astrophysical data. If they would have realized that this is that is not a very good way of starting looking for it. Let me just tell you about it. I mean, so what is the evidence for dark matter? There's indeed a lot of evidence for dark matter, but if you really interpret it, it's clear that there's something wrong with the way we think about it now. So the most direct evidence the first evidence came by looking at galaxy clusters and the way they look at the way they move with respect to each other. And you can assume that they virialize. That means that you look at velocities, and those velocities tell you something about the gravitational potential. Then these velocities were much larger than you would have expected on the basis of what you see as the distribution of matter. So the only way to explain it is that there must be more matter. The easiest and actually best analyzed examples are galaxies. And in particular, the galaxy rotation curves. So a galaxy is an object where you have matter sort of in the center. And then you look at stars, how they rotate. I mean, there's a bulge. They're really, most of the matter, it's baryonic matter. That's going to be in the center. But you look at the velocities of objects rotating around it using Doppler shifts. Now, Newtonian Dynamics would tell you that v squared over r just goes like gm over r squared. If you would only take the baryonic matter, you would expect the velocity profiles, v as a function of r, to do something like this. It goes up and then it goes down, because you see, there's a 1 over r here. If the mass is mostly in the center, this v squared goes like 1 over r. But what's being observed is, instead of going down, it stays constant. Something more like this. So there's a certain discrepancy which is very large, actually. This is associated to dark matter. So that means that we're going to think about the matter here as being made out of two components, baryonic matter and dark matter. And the dark matter has to explain this phenomenon. Now, if you do this for a galaxy like ours, you can calculate how much dark matter we need. Turns out the ratio of baryonic matter to dark matter in our galaxy is about so 1/30th of the matter in the galaxy is baryonic matter, 1/30th. Maybe I should have started by telling you that what the current model is for cosmology. Cosmology has this pie diagram where we think there's about 73% dark energy, and dark matter is about 23%, and then there's 4% baryonic matter. That means if you look at, so this is baryonic matter, or ordinary matter, this is dark matter. This is about 6 times that. But in a galaxy, we see that the amount of dark matter is about 30 times baryonic matter. What would be an explanation? The way that people think about how galaxies are formed is that dark matter forms a potential well, and then the ordinary matter falls in. And then it must be, to me, clear that you would expect more baryonic matter in the areas where there's dark matter. It's not how it's observed. The phenomena that people say are responsible for it is supernova explosions or things like that, which blow out the ordinary matter, but don't blow out the dark matter. There are even dwarf galaxies where you can also do the same.
You're talking about what? The cosmic problem?
No, the missing baryon problem. So the fact that in a galaxy the amount of baryons is much smaller than what you would call the cosmic ratio. Cosmological, we have about...
There's a lot of cloud. Dust.
Not in galaxies.
Yeah.
Now, if you count the baryonic matter in galaxies, people agree with it. The matter cannot be in baryons in the galaxies. They must really be outside of it.
There are a lot of variants outside the galaxy in the intergalactic medium. Yes. Is that what you're saying?
There must be intergalactic, yes, but if you count how much you see there, they don't even add up to what we think there should be cosmologically.
So measured.
What is very well measured is how much baryonic matter in galaxies.
That's well measured.
Yes, and also in dwarf galaxies you find that there's about 1% baryonic matter, 99% is dark matter. So they're really dark matter dominated. In a dwarf galaxy, actually this curve doesn't even look like that. It sort of goes up and then sort of flattens out. But anyhow, there's flattening of these rotation curves, which is quite hard to explain from a dark matter scenario. But the fact that, as I say, there's very few baryonic matter compared to the cosmological data, expectation. And indeed, there are mechanisms that may sort of expel those baryons from galaxies. But what's really surprising is that there is a relationship between the velocity that I see here and the amount of baryonic matter. There's a scaling relation. Which is very well observed, that v to the 4th goes like the amount of baryonic matter in a galaxy. And this is done for many, many galaxies. And this is very hard to explain if you want to say what is dark matter doing that makes this sort of happen. And the measurements they do is this really, you have a curve that if you plot it, v, well, log v to log m, because they do it usually in many orders of magnitudes, and you have, of course, some scatter around it, but there's a very well-defined relationship between these two. This is called the baryonic Tully-Fisher relation. And you can even measure the constant in front of it. There's a proportionality constant. And when you measure it, it actually can be written as follows. I'm going to write it in a very precise way, but this is what's consistent with the data. 30 minutes. Okay. This is what people see. One way this has been explained is by thinking about this law and saying, well, let us forget about the dark matter and just write down a relation, which is sort of the same relation as I had over there. And then I divide by some, well, what I call A0. A0 then is C times H naught over 2 pi. It's the same formula, sorry, here it must be square, as this one. But people have, that's the modified dynamics, Newtonian dynamics I did. People have tried to fit curves using this equation. Because what they say is if I look at the galaxy, I can even integrate all of the baryonic matter up to a certain radius r. So then this m becomes a function of the radius, and you can look at the velocity v as a function of r, and you still can fit quite well what's going on here. There's some features on this which are fitted quite well, very well actually, phenomenologically by a simple relation like that. So how is that related to the ideas I've been talking to you about? By the way, I should say something. I mean, there's a big difference between galaxies and clusters. Galaxies have most of the baryonic matter in their center. Clusters are much more diffuse in terms of baryonic matter, and they're not able to sort of see a similar relationship there. Although it works, well, there are still things that you can describe. What I'm going to tell you now is how to interpret this phenomena now from the ideas I had on the board before. So what I'm what I'm proposing is the following. The baryonic matter that's what corresponds to the matter on the Coulomb branch. As I said, I mean, these are these eigenvalues. This I'm going to represent effectively by Newtonian dynamics. Just ordinary Newtonian dynamics. That means I'm going to think about just baryonic matter density, rho b, as describing the matter distribution of, well, ordinary particles. The gravitational energy, however, has a contribution also from the gravitational field. I hope it's readable actually, but. And a coupling to the baryonic matter. So this is describing how this system would interact if I would sort of think about it as working ordinary flat space. However, this system is embedded in a much larger system, which is the dynamical system sort of describing our entire universe. So I'm thinking about that matrix as a small matrix here in a much bigger system. And this system is described by, well, the Higgs branch. But that Higgs branch is exactly the system I started from. It has the thing that describes the Sitter space. So what I want to interpret this occurrence of this constant in here is going to be related to the temperature of the system here. So this is a system which has a finite temperature, and I'm only looking at a small galaxy in that, embedded in this much bigger phase space. So what I'm going to do is think about this system as being immersed into a thermal situation, thermal heat bath. And the temperature is going to be precisely the Sitter temperature. So let me do this and simply consider a partition function of this system in such a thermal heat bath. So I'm going to write the following thing. I'm just going to take this energy and put it in a thermal system with temperature equal to the de Sitter temperature. And now I'm going to calculate what happens. So what's my interpretation here? First of all, clearly the way that the geometry appears, and even where we want to think about how inertia appeared, I mean, what I said, I'm going to think about the eigenvalues as being sort of coming out of the dynamical system of the Sitter space, of the Higgs branch. Inertia is derived from the Higgs branch. It's derived from the interactions with it. But the Higgs branch has a finite temperature, so I have to be able to see deviations due to the finite temperature. That's really where this whole entropic idea sort of should give its predictions, is that there should be deviations from the normal Newtonian dynamics having to do with the finite temperature of what's going on the Higgs branch. So I'm going to calculate this. Now, it's clear that if you do a minimization of this energy with respect to phi, you get the usual Poisson equation, namely there's a 4 pi g rho b. This is just sort of the equation of motion that you would get from such a, well, minimizing that energy functional. So this tells me that if I would calculate in here the expectation value of this Newtonian potential, it would be equal to the baryonic Newtonian potential. What we see here is actually that we don't have just this, we have a v squared over r being the baryonic gravitational potential, plus there's a dark matter component. I'm claiming that if I calculate the fluctuations due to the thermal states, I get a contribution from the 2-point function. So the fluctuations must come from here. So here I define this 2-point function by subtracting the 1-point function. I'm claiming this is going to be equal to that. So the dark matter can be interpreted as due to the finite temperature of the de Sitter, of the de Sitter space, but actually describing the Higgs branch. And let me do this calculation.
The Higgs branch has finite temperature.
Yes, it's described. It is.
In this her starting point, which is some excited state, you're describing thermal ensemble.
So yes. So the idea I'm gonna calculate. Okay. Yes, it's a thermal ensemble. That's right.
So the starting point is some kind of microscopic quantum mechanical phase space.
Yes.
With a Hamiltonian.
Yes.
And a starting ensemble of states.
That's no.
As opposed to two.
No. It's just a random state, of course. And if you think about the dynamics of the underlying system from the point of view of your, I mean, if I want to know how this influences the dynamics of the slow variables that I'm seeing, this is just a fast set of variables that I can integrate out. But if integrating out is sort of like the same as what you would do in a thermal situation, I mean, there can be an influence of the phase, of the dynamics of what's going on here. And an ensemble is just a trick of calculating the effective dynamics of some underlying system if I know something like, I mean, anyhow, for a black hole, you can have a black hole in a pure state, but we still can associate a temperature to a black hole.
Well, we're still trying to understand that.
For me, I mean, the idea of using an ensemble to try to describe a thermal system is not telling us that it is a mixed state. It's just a trick of calculating what a random dynamics would look like if you're not interested in the microscopic details of that state. So for me, the fact I'm calculating here is independent of whether this is really a thermal system or whether it's just some...
Almost all universities
Um,
I mean, you haven't given the rule what the state is, so it's random. Since there's no rule, you're just saying almost all universes.
I know that if I would apply the general principles we know from string theory, if I want to describe the microscopics in terms of some microscopic sort of dynamical system, that dynamical system will behave as if it's a thermal heat bath with a de Sitter temperature. I mean, it's clear that we would have to change what we know about string theory if we are going to deviate from a microscopic system with that temperature. So I'm just assuming that I have a dynamical system with a temperature given by that, well, what we think it should be, namely the de Sitter temperature. try to decompose. So in that sense, it's not business. I mean, you just get it from the equivalence.
Except for the bullet cluster, this kind of separation. Is aside from that, there's a theoretical bias towards CCMs because of the simulations that like structure. I mean,
that's exactly why I start talking, but that's why I start talking to people here. It's not that interesting.
Well, they're interested. You're not.
No, actually, if you look at what they do, they fit profiles which don't describe it. But they have some preferred profile, and they have many knobs that they turn in order to get something that looks like a galaxy, and then they have too much substructure, and they have satellite problems, and they have cluster problems, and they have. So it's clear that I mean, it's not a convincing story at all, and they're not using a lot of this.
Actually, is first, very. The structure of matter of the universe, dark matter and ordinary matter, or dark matter, say, is not what you might guess earlier. A lot of to get that those elements.
So I'm telling you what.
Anyway, they do a pretty good sort. Now, to do that down to the level of the structure of the center of galaxy, all the problems they have. Is asking the hell of a lot, and it's mixed up with many complicated physics. So let's be kind. They were convinced. You know, this is a debate that's going on for decades.
But they're not using the fact that it's a particle. And I'm telling you, could be.
You're saying
there is stuff, and I think it's more like membranes. So membranes
anyone
would
tried? Anyone tried to not just do the static
the dynamics.
And why do you do the same?
Sorry, what is used in dark
We
matter?
try to take this idea and start with z equals 1,000 and derive the present galaxy, even exclude these differences.
So I have the dark matter component. Namely, I do have matter, not matter which I think of as particles, but there is a part of the energy of the system, mass of the system, that I described in these variables. So there is an amount of stuff that can form gravitational wells and do the same thing that people use in cosmology. In cosmology, the way the dark matter is used uses very little, actually nothing, about the fact that it's a particle. The simulations that people...
It's all by point particles.
No, they have...
Those are the simulations.
No, simulations are with thousands of solar masses. Their particles weigh thousands of solar masses. And this is their simulation. So this has nothing about the 1 GeV or 8 GeV particle. Simulations have nothing to do with particle. And their simulations, as I said, and actually even the person doing it, Frank, I think, is telling people there's something we don't know that has to do with substructures, and there are all kinds of things that they cannot fit. And the other problem is really a problem.
So you're saying, thinking of this as thermal fluctuation of the Higgs branch.
No, what I'm...
Would give rise to the same dynamic,
what I calculated for you, and actually this is why I had to make it clear, mostly here. So I didn't calculate for you the amount of dark matter directly. What I calculated for you is the effect of the amount of dark matter on the matter that we see. So the processes that are responsible for that, I think, is the fact that the ordinary matter has to be gone from the Higgs branch into the Coulomb branch, and that drags along other stuff. And the reason is that the way it has to enter from the Higgs branch into the Coulomb branch is through a non-Hawking interface. And what we see in dark matter is the remnant of that. And that is still there. And I only did this calculation to calculate how much of this stuff is there. But this stuff has its own dynamics. It's like more membranes. And it can do the same things that you would like that dark matter would do. Those filaments and everything would be there, basically because of the presence of this stuff. So I think dark matter is the remnant of the fact that the ordinary matter had to exit the Higgs branch into the Coulomb branch. And we have some stuff that's in between, and the amount of it we can calculate. And then we know how it behaves if we know how it many relations that have been observed that are simply explained by one formula. And I think that cannot be sort of ignored. I mean, this really, I mean, if you can say, well, a theoretical idea, well, most people say it's tested by the data. Here's a formula.
Is there any observable consequence to the fact that all dark matter is not a medium?
I think about it as a membrane, so I think I would like to have a non-local feature.
Maybe that's this way of thinking about it.
How would it interact? It moves.
It would have, a lot of interactions that arise between particles that are dragging outside the horizon. We call non-gravitational interactions.
I think the fact that it has a very different type of description than what I would call 3D here. I think, okay. I think
that's
it's
experimental fact about that. It doesn't interact while you do it. That's an experimental observable fact.
It is kind of
People like to worry about very interactions at a very weak level, but that also doesn't interact with these point matter, whereas here it obviously does interact. And you're saying it's all gravitational, but all the other forces of nature arise from the same process. Why does this?
The forces of nature act on the matter in a way, in a similar process, but this is not ordinary matter, and it's clear that it has a very different description. So, but you would say that this also would feel.
Well, if it doesn't, that's a very.
That's
why it's called.
Let's add this to the list of questions you may still ask about it. Fine, but I think
Why is it dark?
I think it's because it's describing a different part of the phase space.
No, that says it could be dark. Why is it dark?
It's dark from the perspective of things that are on the Coulomb Branch. And it's a separation in which part of the phase space is.
That explains why it could be dark, why it could be different than the particles. Other forces.
But dark means it doesn't interact with photons.
Doesn't interact with quarks.
I think that this way of doing it may have. I think that there's a very natural